Okay, so we have a problem here. We have, it looks like a truck and a trailer. So we have a set of 4 loads at various distances. They're going across this 15-meter beam. And at C is a splice. So we're interested in the moment at that splice. So that's a good application of influence line. So the first thing we'll do is draw the moment influence line, or the moment at C, the influence line for the moment at C. I'll spit it out here in a second. Then once we get that, we want to let the truck move from left to right or right to left and find which combination or which position creates the maximum moment at C. Just to draw your attention, this particular problem has a little odd twist in that there are 2 beams, so only half the load, so half of these values will be transferred to the beam. And there's a couple different ways you could look at it. You could divide all these by 2, or you could just work the problem, and when you get to the very end, divide the final answer by 2. Either way would work out. So let's start first with finding the influence line for the moment at C. Now you remember, well, when we use the Mueller-Breslau principle, we would imagine that C is a hinge, which is a momentless connection, and then we would apply positive bending moment at that connection, and it should deform and give us the quantitative shape of the influence line. So is point C going to move up or down? It will probably move up, yeah. And since it's a hinge, it's held down at B. So you can see the deflected shape of such a structure would look something like that. So very quickly, we could then look at the moment at C and draw our influence line. So there's where B comes down, here's where C comes down. So again, our influence line, the qualitative shape looks something like this. So all we really need to do is find this value, and we'll have the influence line, and we'll be ready to find what combination of these moving point loads will create the maximum moment at C. Now, what does this value imply? What says that's the value of the moment at C when the unit load moves around and is right there. So that would be a problem that looks something like this. I would still have a roller at A, so that's a reaction AY. I have a pin at B, so I have a reaction there, BY. And then I'm looking for the unit load to be at this position, which would be about right there. So that position, when the unit load is 10 meters from A or 5 meters from B, that situation would give me this value. So now I'm looking for the moment at C, which is really right there. So I'm going to cut the structure there, right? So I'm going to cut the structure at C. Which side do you want to work? Do you want to work the left side or the right side to find the internal moment? Right. Well, I heard right first, so we'll do the right side. If I do the right side, then what do I need to know? I need to know the reaction at B. So how do I find the reaction at B for this free body? We'll just take the moments about point A. And I'll use right-hand rule. We'll make sure everything's in equilibrium. So about A, the unit load is positive or negative moment? Negative moment. So it's -1, and its moment arm is 10 meters. And then BY about A creates what kind of moment? Positive. And that has a moment arm of 15 meters. So it looks like BY is then equal to 2/3, right? Well, 10 divided by 15. Okay? So then now, as advertised, I'll draw the free body diagram of just that 5-meter piece. Now, we found BY already. It's 2/3. And now I'm looking at the internal moment there, which is the moment at C. So how do I find the moment at C? take the moment at the cut. So I'll again use right-hand rule for my sign convention, and I will sum the moments about the cut that we just made. Make sure it's in equilibrium. So let's account for that. Starting here at the cut, this moment is positive or negative with my sign convention? Negative. And then this 2/3 force about C is positive or negative moment? Positive. So the force is 2/3 and the distance is 5 meters. So it looks like the moment at C is equal to 10/3. And that's 10/3 meters. So the unit now becomes meters, and this value will be 10/3. Okay? So that's how we can do the moment. The influence line. So any questions about that? Okay, so let me just drop this other one on top, and now we'll look at the actual maximum that can be developed. So flipping back just quickly, I've got 4 forces to deal with, so I'm going to have really 4 cases. 4, 6, 2, and 1. And what I'm going to do is make it easier for myself. I'm just going to work this problem. When I get to the end, divide by 2. So moving from left to right, let's examine the influence line for a second. If my forces are on the left side of this influence line, if I move 1 meter to the left, is this ordinate larger than the value 1 meter to the right?
Yes.
Which one has the smallest slope? The left side. So that means the ordinate values are higher. So anytime you can have more of your forces on the left side, you're probably going to be better off. You guys see that? So right now when I'm going from left to right, when I'm having the bulk of my forces really inhabit the left side, it's probably going to be larger than if I turned it around and my truck drove from right to left, where then the majority of the forces would be here, and then they would cross over. So I don't know if we'll have time to do it all, but just to make it easier today, you could do it with enough time. You would have to, you would run the truck from left to right, and then you have to turn around and run it from right to left. You could do that. That would be 8 cases to do total. That's too much for this problem. So let's just do as it's drawn. Let's just do left to right for right now. Okay? So just to help me get started, I'm going to lost my let's do the first case right here. So I'm going to assume case 1. Sorry, my production quality is not very good today. I did do one thing right. I went and bought my Christmas tree yesterday.
So did you? Wow. Is that awesome?
It's huge.
Is it real?
Is it real?
Mr. Wynn.
Is that your North Carolina tree?
No, mine comes from Michigan. It's a Fraser something. You know what it is? It's a wallet drain is what it is. I don't know. I need to get in the tree business. Anyway, I put it in a bucket of water, and it drank half a gallon of water in the first day and a half. It was thirsty. Hopefully it'll last to Christmas. Since it's still November, right? What in the 2 years ago we kept our Christmas tree up all the way to Valentine's Day. Huh?
I should do that.
How? You just leave it there. You just walk by it. It's real easy to do. All right, so what I'm going to do is kind of redraw this thing down here. All right, let's see if I can do this. maybe not quite to scale. So we know this is 10/3. So I'm going to now let my truck drive over to the first force, the 4 kilonewton force is here at the max value. And then 2 meters back, I have a value of 6 kilonewtons. 1 meter back, this is not to scale, another 2 kilonewtons. And then 1.5 meters back, a 1 kilonewton force. So this is 2 meters, 1 meter, 1.5 meters. So what I've got to do is I've got to find all these values on my influence line that correspond to those positions. So before we get started, what's the slope of the line? Well, it's the rise over the run, right? So I have a rise of 10/3 over a run of 10. So what's that? That's 10 over 30. That's 1/3. Right? So that means for every meter that I go over, I drop 1/3. So if I go over 2 meters, I should drop 2/3. 10/3 minus 2/3 is 8/3. See that? Then I go over another meter, so I drop 1/3. 7/3. Now here's the tricky one. I go over 1.5 meters,
11/6.
so I drop 1.5 which would be what?
11/6.
We could do it that way if you want. Is that right? 11? Yeah, 5.5. So that's 11/6. Yeah, that's cool, isn't it? So what is the moment at C for this first case? Well, let's just start from the left and move to the right. So I'll have my 4 kilonewton. Remember, all these values are in meters. So the first one would be 10/3 meters plus 6 kilonewtons times 8/3 meters plus 2 kilonewtons times 7/3 meters plus our favorite one, 1 kilonewton times 11/6 meters. So what's all that?
Are you going to multiply that by 1/2?
Oh, we can't. We're done.
No, not, I mean, like, because it's triangle.
No. That would only be if it was a distributed load, right? So point loads, it's the value of the load times the ordinate value. That's why we picked off these values right here. I don't think, does this have a dead load or a live load? It does not. So if I did have a uniform load, for example, if this problem said, hey, there's a 1 kilonewton per meter uniform dead load, then what would you have to do? You have to find the area under the curve times that load intensity and add it. But we don't have that. Does anybody get a number for that?
35.83.
35.83. Anybody else get that? No? Are we going to go with what Mr. Grand did? You don't know?
Yeah, I got that.
Who said that? Okay. So was it 35.83?
Yes, sir.
And that'll be kilonewton meters. We would. I'm going to wait to the end. Okay, 1 case down, 3 to go. So now I'll bring on my other page. And we'll try to pick up where we left off. So this would be case 2.
We won't get something like this, will we? Unless it's like, this is going to be 2 wheels.
Oh, you might get something like this, but I don't think I'd give you 4 to do. I mean, that's excessive. 3 would be borderline, 2 more likely. It's the same idea, though, right?
One would be optimal.
One would be optimal. Yeah, one would be optimal. That would be Mr. Santana on the unicycle. I may have to revise my test and find a little symbol of a unicycle and find a Mr. Santana picture and put him on the unicycle. All right, so here's our moment at C, and there's our influence line. You might remember that this had a value of 10/3. So now the middle load, which was, let me revise it, that was 6 kips. So 6 kips goes to the top. Not kips, kilonewtons. And 2 meters in front is the 4 kilonewton. 1 meter back was the 2 kilonewton, and 1.5 meters back was the 1 kilonewton force. So now I need these values on my curve. Now we know the top here is 10/3. We already found the slope of this side. Remember, it was 1/3. So I go 1 meter back. I'll drop 1/3. So this will be 9/3. And then we'll have our 1.5 back, which would be 7.5, or 15/6. Now we do need to worry about this one in the front. Because what's the slope of this guy?
2/3.
Well, rise is 2/3 still, but the run now is 5, right? This was what did I say? 2/3. It's 10/3. 10/3 over 5. So that'll be 5 over 15. I'm sorry, 10 over 15. So that's 2/3. So if I go 2 meters, that'll be 4/3. 10/3 minus 4/3 is 6/3. Okay? So now the moment at C for case 2 will be 4 kilonewtons times 6/3 meters plus 6 kilonewtons times 10/3, and that's meters, plus 2 kilonewtons times 9/3 plus 1 kilonewton times 15/6 meters. So what's that equal to?
I got 36.5.
36.5. Anybody else get that? 36.5, and that's kilonewton meters. That's slightly larger than the last case we had. So far, this is the case that's ruling. All right. So for me, on an exam, I think this would demonstrate that you understood the process. So I wouldn't expect more than 2 or 3 loads at the max, not 4, 5, 6, 7, multiple directions. That just seems excessive. But we're not in the exam, so case 3. Let's see what we got for case 3. So again, I'll resketch the influence line for the moment at C. I forgot my units here. These are meters. And now we'll let the third load go to the top position. So in that case, it'll be 2 kilonewtons there. And then a meter forward is 6 kilonewtons. and then 2 meters forward, gotta make sure I get it to land on the, is 4 kilonewtons. So that's a total of 3 meters, and remember this distance was 5 meters. So it's still on the structure. And then 1.5 meters back is our 1 kilonewton force. So these are the positions that we need ordinate values off our influence line. Again, we still know this value is 10 thirds. Now we know going backwards it's 1/3, so that would be 1.5 thirds, which would be 8.5 thirds, which would be 17/6. The slope this direction is 2/3, so I go 1 meter, that I drop 2, so this value would be 8 thirds. Another 2 meters, I would drop 4 thirds, so this should be 4 thirds. So now the moment at C for case 3 would be 4 kilonewtons times 4 thirds meters plus 6 kilonewtons times 8 thirds, that's meters, plus 2 kilonewtons times 10 thirds meters, plus 1 kilonewton times 17/6. I just noticed I wrote thirds there. That's sixths. What's that?
30.833.
30.833? Okay. So we're getting smaller. And you can probably see that if we went ahead and did the fourth case, which we will, just to be complete, that this first load will it go off the structure?
Yeah.
No, just barely. It'll just be barely on. But they'll all be on the lower side, so I imagine it'll be smaller. So we've probably already found the one that's critical. But let's go ahead and finish this to be complete, and then we'll just to check. So what I'm going to do this time, though, is I may draw it just a little bit bigger so that I can squeeze it all in. So now the last load of our trailer shows up at the top. That's our 1 kilonewton. 1.5 meters forward is the 2 kilonewton. And then another meter is the 6. And then 2 meters is the 4. So now all of the ordinate values on the right side. So starting at 10 thirds, we know the slope of that side is 2 thirds. So this will be 2.5. That'll be 3. Is that 3 thirds? Right? 2.5 would be 3 thirds. Is that right? So 3 thirds from 10 thirds is 7 thirds, and then 2 more will be 5 thirds, and then 2 there would be 4, which would just bring it down to 1/3. Did I do that right? Okay, so I think we already know what this is going to give us, something smaller, but let's go ahead and calculate it real quick. So I've got 4 kilonewtons times 1/3. That may be the smallest value we've had so far. Plus 6 kilonewtons times 5 thirds. Plus 2 kilonewtons times 7 thirds. Plus 1 kilonewton times 10 thirds. What's that?
I got 19.33.
Anybody else get that? Okay, cool. 19.33. And that'll be kilonewton meters. So again, it looks like this is the highest value, so I'll double underline that. Now to actually solve the problem, we would just divide this by 2 at the very end. Okay? That was kind of long and painful. The video was 25 minutes long, so obviously that doesn't qualify for a test problem.
Dr. For the first case, why did the 4 kilonewtons stay on
Well, the distance between there, that's 1.5 plus 1 is 2.5 plus 2 is 4.5, and this distance was 5. So it just stayed on. But that is something to consider. Depending on these spacings, sometimes these values will go off the structure or haven't come on yet. Just depends on the problem.